but he looks to me as though he's a pretty active sort of guy. So I think we're really privileged to have you along here tonight, Renee. So I'll hand over to David Strange, who will be the host for the meeting. So we look forward to this. Okay.
Thank you, Bob. So yes, if everybody could mute themselves, I think most of us have. So Rennie, it's over to you. If you'd like to share your screen, we're all ears.
Yep, excellent. Let me just kick start it. Okay, I'm hoping you can all see the screen share properly.
Yeah.
And is the audio all right as well?
That's fine, thank you.
Okay, yeah, I see some thumbs up, that's good. Yeah, I'll just locate the windows in a good place for me. Great, yeah, I was trying to get the my little face in the corner, but I'm not sure. Oh yeah, I think it might work. Something like that. So you might even be able to see me whilst I'm talking. Okay, good evening, everyone. It's a pleasure to join you online tonight. I must confess, this is the first talk I'm giving over Zoom, so I'm hoping that the technology will work well, but also that I will deliver something interesting to watch and listen to. It's really strange because I basically spend my entire days over Zoom in meetings and whatnot, but I haven't given an actual astronomy talk through it. It's mostly for teaching and other purposes. So the talk I wanted to give you tonight is about Einstein's relativity and how we can use pulsars, which is the type of objects that I study for my research, in order to test Einstein's theory of relativity. So now, obviously, I think someone's trying to talk. Perhaps I'm not sure if it's.
Yeah, can you put it on the full screen, not the?
Yeah, I'm not sure how that show. It should be. Oh, sorry. Oh yeah, sorry about it. I think it might have. You might have got the wrong. Sorry. New share. Yeah. Okay. I think is that good like that? Yeah. Sorry. I think it changed or something as I was setting up. Okay. Yeah. Thank you. Okay. So. Yeah, so I think my face has disappeared, but that's all right. You can probably see somewhere else. Okay, so yeah, so obviously relativity is something, in Einstein's theory is something that sounds, very difficult, and we basically hear about it in either science fiction movies or in when we hear about like the late Stephen Hawking or whatnot, talking about like very complex theories. And I must confess that, yeah, it is not so easy, but I believe it's possible to actually explain it in a way that, mortals like you, but also myself, can actually understand. So I'm not a theorist. So what I do is mostly observations, but I try to link my research to the theory, basically, and try to confirm or invalidate theories. So my talk is basically in three parts. The first part is I'm going to explain to you a bit about pulsars and the basic of what you need to know, really, so that we can then talk about gravity and Einstein's relativity in the second part. And then finally, we'll put the two parts together, the two elements, and we'll see how we can use pulsars to test relativity. So first round is about pulsars. So we could spend hours or days talking about pulsars, really. But tonight I'll just tell you the very minimum. Perhaps by show of hands for you on the call, who has heard about pulsars in the audience? Okay, so sort of maybe 2/3 or maybe half of you. So it's quite impressive. I mean, pulsars tend to be a bit less mainstream than black holes or stars or galaxies or nebulae. So pulsars are a type of neutron star. So the neutron star is the object. They are very tiny. We're talking about objects that are something like 10 kilometers in radius. So the size of a small to medium city. But they can hold as much as more or less 1.5 times the mass of the sun. So you can imagine, the sun is way larger than the Earth, right? You could put 109 or 110 times the Earth next to each other, line it up to equal the diameter of the sun. So sun is way larger than the Earth, like volume-wise, but also in terms of mass. Yet you could take 1.5 times of it and shrink it down to the size of a city. And then that object happens also to be extremely magnetized. So what I call B field is the shorthand for a magnetic field. So just like a magnet. And pulsars, the little object, has a magnetic field with a north pole and a south pole, we believe. And if you look at how powerful this magnet is, the units we use in pulsar or astrophysics is called the Gauss, after the physicist who studied magnetic fields. So 10 to the 12 Gauss. So what this number means is basically 1 followed by 12 zeros. Okay, so it's a really large number. Okay, so that's why we use the exponent notation. So 1 followed by 12 zeros, Gauss. Now, 1 Gauss, you're probably not very familiar. We know about meters and miles and even maybe amperes and other units like that, but Gauss is not something we talk about very often. So the field, the magnetic field on Earth is roughly about half of 1 Gauss, okay, so 0.5 Gauss. So this means that the magnetic field of a pulsar or a neutron star would be something like 1,000 billion times more powerful than the magnetic field on Earth. Okay, so to give you an idea, the most powerful magnets that we can achieve on Earth, like for even more powerful than the ones that are used for like scanners and medical imaging, they can reach maybe a few kilogauss, so a few thousands of Gauss at most. So we're talking about billions of times more powerful than anything we can achieve on Earth. So it's really impressive. But on top of that, the object, the neutron star, can spin. And as it spins, the light that it emits actually can actually flash as seen from us. And this is what we call the lighthouse effect. And it's due to the fact that most of the light that's emitted by the star does not come from all over the surface, like a regular star would emit light, from it's hot, and like the sun, for instance, the whole surface emits light. But rather, most of the light does not come from the surface itself, but it comes from that large magnetic field that surrounds it. Inside of it, there are particles. So you can sort of picture it as a bit of some kind of a strange kind of, we would not even talk about an atmosphere, but it would be particles that are trapped in this giant magnetic field. And these particles that are trapped in there, some of them will basically follow the magnetic field, and some will actually escape through the poles. And as they escape, they emit radiation. And most of the radiation they produce is actually radio waves. So it's not optical, it's not light that we see with the naked eye, but it's actually light that are radio frequencies. So like the ones you can tune on the radio. So you can picture the neutron star as basically some very tiny object, and it emits light like a cone, a very beamed directional cone of light. And so as the star spins, basically you can imagine that you would see a flash of light when that cone sweeps across your sight line. And that's because the axis of rotation and the axis about which the magnetic field is oriented are not necessarily the same. Just like Earth, right? So as you probably know, the North Pole of the Earth and the magnetic North Pole are not exactly aligned. So, and it drifts a bit over time, as it turns out. So right now, the magnetic North Pole is somewhere like in the northern Canadian islands. So there's an offset between them. So because there's an offset, you have this lighthouse effect. So when we see a star flashing like that, we call it a pulsar, because that's the contraction of the word pulsar, pulsating star, so which were put together as pulsar. So the neutron star is the generic type of object, and the pulsar is a neutron star that pulsates. And there are some pulsars that we don't see, there are neutron stars that we don't see as pulsars, but they tend to be rare. So most of the objects we see, they're the ones that flash like that. So where do these pulsars, or even like the neutron star, comes from? They're basically produced by the death of a massive star. So for stars that are something like 8 times or more than the mass of the sun when they're born, when they end up their lives, they will expand in a supergiant and they will explode as a supernova. So it's a very sort of catastrophic type of event, which produces as much light within an energy within a few seconds as the entire sun will produce during its entire lifetime. So very powerful catastrophic event, and maybe even some of you as amateur astronomers might have observed perhaps supernovae or seen sort of pictures of supernovae in magazines. So these basically you observe a galaxy typically, and then all of a sudden there's this new source that appears, and after a couple of weeks it fades away. So stars can also explode in our own galaxy, and but they don't do so very often. So we believe that on average about 3 stars like that would explode in a supernova every century. So they're rare phenomena, and most of them actually, when they explode too far from the Earth, like say on the sort of on the far side of our galaxy, such that we don't even see the event, or at least we don't see it with the naked eye. So only the ones a bit closer do we see. And actually, we're kind of overdue, because we haven't seen one, properly speaking, in our galaxy with the naked eye in something like 150 or 200 years. So it's been quite a little while. Now, the image you see right there is the Crab Nebula. So how many of you have observed the Crab Nebula? So it's Messier object M1. Right? So for those who chase the Messier objects, so I've seen it. I've seen all of Messier objects. Actually, I've managed to. Before being a professional astronomer, I was also amateur astronomer. So I built my own telescope and everything, and I did Messier marathons a couple times in the spring, and I managed to see something. I can't quite remember, but something like 70 of the Messier objects in one single night. So never quite managed to see them all. It's very challenging for some of them, as if you've ever tried. But I must say, though, I've seen them all, but using a Dobsonian telescope with no go-to function and GPS, or so finding everything by hand. So no cheating. Was there a question? So I could hear, I think Pete saying being impressed maybe, or something. So what you can hear now is the sound of a pulsar, and that pulsar has been observed with the Jodrell Bank telescope. So when these stars rotate, right, you see the beam flashing. So you could imagine, if you were able to make a picture, you could see the star getting brighter and fainter. However, when we observe with radio telescopes, such as the Lovell telescope at Jodrell Bank, it's not possible to see an image with the Lovell telescope. So you might not know that, but the telescope we have at Jodrell Bank is a 1-pixel telescope. Okay, so basically the light comes. I mean, it's essentially a big bucket, right, that collects light to see very faint sources from the sky. But it's, in a way, it's not so much different from, you know, rabbit ears or, you know, from the antenna in your car. So it just captures the radio waves, converts them into essentially a voltage. And then what we can detect is actually a time series, like a stream, a bit like a cardiogram, if you want, of voltage as a function of time. So when you look at something that varies over time, like a pulsar, then you can see the variability. And so you essentially, what we see with the Lovell telescope is more like a heartbeat than an actual star, you know, that flashes. So it's more like a cardiogram, an electrocardiogram that we observe for pulsar. So the data that you see there are actual real data from the telescope of on that, you know, particular source. But most pulsars actually are too faint, so you don't really see each individual flash of light. You kind of need to accumulate them, and I'll display an example of that in a few seconds. But the Crab Nebula, the reason why I'm showing it is because it's one of the most famous pulsars that's located right at the heart of that nebula. So right there where my cursor is, you can see there are two stars. And one of the 2 points, the one that's on the upper part, if I recall, I keep mixing them up because obviously there's no up and down in space. I think it's that one. Actually, if you could take an image like really quickly, you know, this image actually was taken by myself at a 1.6 meter telescope in the southern part of the Quebec province in Canada, where I'm from. It was when I was an undergraduate student. I was doing a project to learn how to do proper, like, sort of science, and we made a pretty picture. But the pulsar in the Crab Nebula spins 33 times per second. So typically when you take an astronomical image, you need to accumulate light for minutes or hours even. So you don't see the source flashing on this image. Well, okay, it's not a video obviously, but still, normally you don't see it flashing, you just see a source. So only with super fast cameras these days are we capable of seeing, of making pictures on like sort of, several hundred times per second, and then we can see the star flashing. But most pulsars we actually observe with radio telescopes rather than optical telescope. So we know something like 2000. I think the number keeps going up. So I think we're getting close to 3,000 now. So in the last year, a bunch of them have been added, and there's about maybe 10% or so of them that actually are not just the pulsar that's isolated, but it's got a little companion star, like another star that orbits it. So it makes a binary system. So like I showed at the previous slide, that we can actually listen to pulsars. If you take the radio signal from Jodrell Bank, right, it's just like listening to the radio station. And actually the frequencies we use, they're not super, massively different from the FM band, for instance. So we tend to observe at like 1.4 gigahertz. So so it's about what, like 20 times higher frequencies than the FM bands. So the FM band is somewhere around 100 megahertz or so, whereas we observe at 1,400 megahertz very often. So here's some pulsar noise. Can you hear the sound?
No, can't hear anything.
You can't?
No, I think you need to
sorry.
share your computer sound.
Yeah, I think I didn't activate it yet. I will do that just now. It worked. So that one is the pulsar that I showed at the previous slide, actually. So it's called O329. By the way, the name, it's just a shorter name, but the full name is would be something like B0329 plus 54 something, and it's basically the coordinates in the sky where we find the pulsar. Because you can imagine, you know, since the most famous ones tend to have like an actual name, like the Crab, like because it's in the Crab Nebula. But most of them, they just have coordinates in the sky because otherwise we could not find a single name for each. Apologies if it's a bit loud. Always sure how the sound comes out. So this one is 0437, so it spins every 5.5 millisecond. And you can see on the upper plot, so that's 0437 is this one right there. So basically the flash of light that's produced, you know, on the sort of like cardiogram chart, if you take many of these pulses, right, and you stack them on top of each other, the shape tends to be very constant over time. So one flash to another might vary quite a bit, but when you accumulate them, the shape that you get, what we call the pulse profile, tends to be very characteristic for each pulsar. Each of them looks different. So it's a bit like a fingerprint, if you want. Then the Crab pulsar, this one. So 33 times per second. So we can't quite hear actually, you know, the individual pulse, but you can see, you can hear like just because it varies a bit actually. Then another one that's quite famous in the Vela constellation, it's called the Vela pulsar. It's 189 milliseconds for one rotation. So I quite like that one because it sounds like the pulse profile. So is actually, it's not on this chart there, but the pulse profile is a bit like this one, if you want. It's got two peaks. So that's why, you know, when the sound plays, right, you can hear like toot 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 toot, and it's a bit like a horse galloping or something. And then this one, 1937, is not very pleasant to listen to. So it's 1.55 millisecond, or basically 682 rotations per second. And this one was the fastest one that we had known, that we knew of, from basically 1981 until 2006. So for more than 25 years, it was the record holder. And then in 2006, we found one that makes 714 rotations per second. So 1.399 milliseconds. So that's really fast. So it spins faster than, you know, a kitchen blender, faster than like a formula engine, you know, basically. But the whole thing is the size of a city, right? So at the surface of one of these objects, you're traveling, I mean, not at the speed of light, but you're traveling at a significant fraction of the speed of light, like something like a couple of percent up to, you know, a few tens of percents in some cases. So now I'd like to focus our attention a little bit. So you know a bit now about like more or less what pulsars can sort of look like and sound like. You can imagine also, by the way, that we don't listen to pulsars when we do astrophysics research, because we would just go completely crazy listening to these like stuck, tuck, tuck, and these, hissing noise. So instead we look at the, those cardiogram charts, recordings instead. And then by measuring like the time between them, we can tell like how fast they rotate. And then there's, all kinds of science we can do, but I won't enter into the very details of it tonight. However, I'd like to tell you a bit about binary systems, because they're quite interesting. So imagine that you have two stars, right? And they orbit each other. And we know it's quite common. Actually, most stars in our galaxy are, either in pairs or triple systems, or even more stars than stars that are isolated. So it turns out, that stars are a bit like human. They tend to not like, being on lockdown and being on their own. So, so they form, in clusters, and often some of them will actually be bound and orbit. So imagine you have two stars. Then the more massive star, which is not necessarily the bigger one visually, but often, when the star gets to the end of its life, it will turn into a supernova. So it will get bigger and bigger, like in a super red giant, and then will explode eventually. So if we look at the animation there, so that's basically what's happening, supernova, and then the star is massive enough, it forms a neutron star. Eventually, the other star will also, grow and become either a red giant, like if it's a star like our sun, or it might become a super red giant if it's a bigger star, and then might explode as well as a supernova. Or if it's smaller, like the sun, it won't be exploding, but at the end of its life, the outer shell of the star would basically expand so much, and at some point will be released from the core of the star. And then the core will shrink and form a white dwarf in the case of the sun. So it's not as dramatic an event, so it's not a supernova, but smaller stars, they don't explode in that way, but they form a compact object, and it's surrounded by this shell of gas. When stars are more massive, instead of making a neutron star, they might turn into a black hole. But you need a star that's typically more massive than the ones that form the neutron stars. So eventually that star can grow, right, inflate. And then if it becomes too big compared to the distance to the neutron star, it may be that at the surface of that star, the gravitational pull from the star itself, right, that holds it together, might actually not be strong enough to counteract the gravitational pull from the neutron star that's around it. So then the matter at the surface will sort of become unbound and might actually start being attracted by the pulsar rather than being at the staying there on the star. So that matter will start essentially kind of leaking out of the star and will be driven towards the pulsar. And as it's driven towards it, because it orbits, it will not go in a straight line, but rather it will come closer on a sort of like circular, like whirlpool kind of fashion. And then eventually it will, go into orbit, and then eventually it will fall onto the surface. So this process, we call it, oops, let me play the video at full length. This process, we call it accretion. So first star explodes, then eventually the other star, it has to be quite close. If it's too far, when it becomes a giant star like that, it will not, the matter at the surface will not leave the surface. It will remain bound to the star. So the orbit has to be sufficiently compact. And then as the mass is transferred, it falls onto the surface. And then it will actually, if you pay attention to the video, you will see the pulsar that's already born starts spinning faster, right? And that's due to a principle that we call the conservation of angular momentum. So basically, you can imagine a bit like a merry-go-round. When you go to, maybe when you were a child, or if you have like, children yourselves or grandkids, or seeing kids at a park, right? They go on the merry-go-round, then they push, then they spin. But normally, because of the friction, they would slow down. But then if there's another kid, right, that runs and then jumps on the platform, right, it gives it, it transfers energy to it. And then it keeps kind of like going, a little faster. And then if more people jump on, right, they each give a bit of energy. And actually, instead of slowing down, you can even like spin up. So that's what's happening when the mass is transferred. And so that's why it turns out that the fastest pulsars that we know, like the ones that spin fastest, are the ones that are in binary system. Because when a pulsar forms, like the Crab pulsar, it spins really fast, something like 30 rotations per second. But eventually it slows down, and then it spins maybe a few times per second after tens of thousands of years. But then if there's a companion star, like in this video, then you can spin it up, and actually then you can make the neutron star spin thousands, well, more like hundreds of times per second. So that's basically the concept of the fast spinning pulsar. the other thing perhaps I should say is that the compact object, like the pulsar, but we call it also the neutron star because the object is so compact that inside the object, it's not normal matter that you would find, but rather it's matter made of neutrons only, which neutrons are some of the fundamental particles making atoms. And basically, when you squish matter at really, really high densities, matter will turn into some soup of neutrons and won't be regular matter anymore. So, so if you were to take basically every humans on the planet, so there's something like 10 billions of us, and you were to squeeze us, like, you know, in very close proximity, like actually you need to squeeze us to the size of a dice, okay, then we would basically reach the density of a neutron star. Okay, so it's about 10,000 humans. The density of a neutron star is about 10 billion humans, rather, per sort of like cubic centimeter or so. Okay, so now you're experts basically on neutron stars and pulsars. Okay, you know enough for what we require for tonight. So now let's move on to relativity. Make sure you remember what I said so far, because there's obviously the exam at the end. Just kidding. Okay, so relativity. So you know this mustachio guy with the funky hair, Albert Einstein. Is very well known, obviously, for his theory of relativity. But as it turns out, relativity is two theories. There is the first theory that he came up with and he published in 1905. That's called the special relativity, because it only applies to special cases. And basically, you could derive like all the equations, like all the, you know, the sort of physics and what happens according to this theory from only two postulates, as we call, so two principles. So what Einstein said is that the speed of light is constant in space and in all directions and for anyone in our universe. That's something that was basically known before, but he basically said, okay, let's take that for granted. And the other thing is that the laws of physics must remain unchanged if you basically are either not moving or if you're moving at constant speed. If you accelerate, then things are a bit different. But if you move at constant speed, the laws of physics should be the same for everyone. And so based on that, he went on with his pencil and paper and then got put together like the full theory of relativity. One of the consequences of this theory is what we call the mass energy equivalence principle. So basically what Einstein discovered is that mass and energy are two things in our universe that we tend to see as different, but in terms of pure physics and laws, they actually are interchangeable. So if you want to basically, I don't know, figure out how much energy is represented by, say, 1 kilogram of matter, then you just put it in that equation. So you take the mass, 1 kilogram, and then you multiply by the speed of light, which is 300 million meters per second, and you square the speed of light. And then that gives you the amount of energy in joules, okay? So with 1 kilogram, you get basically billions, I forgot like exactly how much it is, but you get billions of joules. So 1 watt, right? 1 watt of energy is 1 joule that's dissipated per second, right? And a typical sort of, nuclear power plant would have a reactor that produces something like a few megawatts or so. So basically 1 gram of matter, if you were to transform it into pure energy, you would be able to produce, as much energy as needed by, an entire country in a full year. And so that's why essentially nuclear energy is so, powerful, because in nuclear energy, either in fission where you split atoms or in fusion, like what is done in stars, you essentially put matter together to make something heavier, or you took something really heavy and you split it. And when you split it, you essentially release some of the binding energy, some of what glues matter together, if you want. And that corresponds to something like a small fraction of order of like a fraction of 1% of the total mass of the object. But say 1% of billions of joules is a lot of joules, right? Is a lot of energy. So basically, in a sort of like nuclear reactor, you only need like a few kilos of like uranium to produce a lot of energy. Whereas in conventional, fossil fuels, for instance, then you're using the chemical energy. You're not using the actual transformation of pure matter, if you want, into energy, but you just use the chemical energy in the molecules. And so the yield is much lower. So that's why, like, a coal power plant would need like a lot, tons and tons of coal to equate what is produced by, a few grams of uranium, for instance. And so that's also why stars are so powerful, because they literally, do the sort of like transmutation, a bit like alchemists would do, right, of elements into other elements, and that releases a lot of energy. Now, let me talk about some of the other consequences. So I've just sort of talked about mass and energy. Let's talk about what the effect is on velocities, from that theory. It's really curious. So imagine you're on board a train, right? And you're going, I don't know, from I guess most of you probably live on the Devon coast, I imagine, if that's where the observatory is located. So imagine you want to come and pay me a visit in Manchester, which obviously takes forever due to our slow trains. But let's say our train travels at 100 kilometers an hour, and let's say that you like archery, whatever, and then you decide to open the window and throw an arrow right at a target on the ground. Okay, and the arrow that you throw travels at a speed compared to you of 200 kilometers an hour. Okay, so by the way, I have no idea if it's a realistic speed or not for an arrow. Maybe someone can tell me, but let's just say that's the speed of the arrow. Now, let's say you have a friend who's on the ground, and that person uses the exact same brand, same arrow, same type of arrow, pulls the bow exactly in the same way. So the arrow of the person on the ground travels also at 200 kilometers an hour. So now imagine that you had like a radar camera or something that measured the speeds, at the target. So what would you say would be the speed from, measured for the arrow from the person on the ground, right? Do you all agree it would be 200 kilometers an hour, right? Because the person is on the ground moving, shoots an arrow at 200 kilometers an hour. So that should be what's, measured at the target. So, okay, that's fine. That's quite in line with we expect. Imagine now for you who's on the train, right? The arrow travels at 200 kilometers an hour forward, but also the train is traveling in the same direction at 100 kilometers an hour. So, okay, so now by sort of like, Roman gladiator style, okay, who says it would be, say 100 plus 200, right, is 300. So who says that the speed of the arrow would be 300 kilometers an hour? So exactly, so finger like this. Who says that the speed would be larger than 300? So thumbs up. And who says that the speed of the arrow would be lower than 300? Thumbs down. And let alone, there's no friction, right? No air friction, not like we're in vacuum. So ideal case scenario. So cast your vote. 300, lower, above. Okay, I got some equal. A few people are down. I don't seem to see anyone who says more. Okay, that's interesting. Yeah. So more or less, right, for an arrow like that, it would be more or less 300 kilometers an hour. So it would be more or less like this. Actually, not quite, but let's see the next example. Imagine that the train travels at the speed of light, Okay, so now we have like, a super, a TGV, like gone, a really fast moving train. And I'm shooting arrows made of light traveling at speed of light. So I could have a laser pointer for that matter, right? So I shine light forward, okay? And then the person on the ground is also equipped with a laser pointer, or whatever, that shoots light at the speed of light. So now for the person that's on the ground, right, the speed at the target should be the speed of light, right? Because nothing is moving, only light. So, okay. Now, for the person on the train shooting light from the train, both of them traveling at the speed of light. Now, we said that the speed would be 2 times the speed of light. So basically speed of light plus speed of light. Who says that the speed would be only 1 times the speed of light? So just speed of light. I'm not sure if there's other options, maybe lower than the speed of light. So, okay, so option 1, maybe just sort of raise your hand, 2 times the speed of light. You raise your hand, okay, no one. Who says exactly the speed of light? Raise your hand. Okay, who says somewhere between the speed of light and 2 times the speed of light? So basically the sort of 2 added together, but not quite. No one. Okay, and who says less than the speed of light? Okay, wow, you're really good students. I'll take you all on my courses. That's right. So the answer is that it would travel at the speed of light. So basically, Einstein said that the speed of light is constant for everyone, but also by definition, it means that nothing can go faster than the speed of light. And everyone, regardless of where they are in the universe or their point of view, should see the speed of light traveling at a different speed than the speed of light. So this means that if you're on a train at the speed of light or traveling even at 100 kilometers an hour and you shine light, the speed that you measure for that light is always the same, regardless of whether you shine light forward or backward or to the side, okay? And this also has like really strange consequences. One is that, for instance, time also does not appear to be the same for people who travel fast than for people who travel very slowly. So if you're on board of a very fast ship or a very fast train, time would actually go more slowly for you than it would go for someone on the ground. So if you were to, I don't know, travel, really far in space at sort of like half the speed of light for, a number of years and come back on Earth, then people on Earth would have aged like some amount of time and you would have aged much less than that. So it's really mind-boggling. So now you start having these things like time, not being quite the same for everyone. And also you start having other things like distances not being the same. So if you travel very fast, distances like in the direction that you're traveling seem to be much shorter than for people who don't travel. I could hear someone unmuted. Is it because there's a question or it was just a fluke? No, okay. Yeah, so I'll just carry on. Yeah, so these things then start becoming, very strange. Now, that's the first theory. That's the one we call the special relativity. There's the other one that we call the general relativity. This one is much more elaborate and essentially deals with pretty much like everything in terms of physics laws of gravity in the universe or motion of bodies. So I said earlier that the special relativity only deals with things that move only at constant speed or don't move at all, whereas the general relativity also encompasses things that accelerate or decelerate, but also takes into account things that are in gravitational fields, so it accounts for gravity. And the best way to describe it is the following. It's basically to say that space-time is this thing in which we live. So there's 3 dimensions of space, right? Forward, backward, sideways, and sort of up and down, right? So that's the 3 physical dimensions. But also there's the extra dimension, which is time. And we tend as humans to see time as something that's completely different. But actually, in terms of theory of physics, you can deal with all the equations and everything in exactly the same way you deal with time as you deal with spatial dimensions. And when you start doing that, then matter in the universe basically is matter that lives in this four-dimensional space-time. And matter basically tells how the space-time, so you can imagine like this sort of like trampoline kind of like structure, right, that describes our universe. If you put matter in the universe, it stretches and deforms our space-time. So basically matter tells space-time how to curve, but then the space-time space-time tells matter how to move rather, but matter tells space-time how to curve. And I'll show you how this works out in a moment. Now, I won't bother you with like lots of equations tonight. I wanted to show the E equals mc squared that you've seen on like probably people going on the beach in Devon, wearing t-shirts, C equals mc squared and all kinds of like things like that. But people wear it and they don't really know what it is. So now you understand it a little bit better, hopefully. But the equations that's there is basically the equation of general relativity. So I won't try to get you all kinds of maths through tonight, but basically in an equation like that, right, there's an equality term. So that means something on one side, like the left-hand side, must be equal to something on the right-hand side. And the idea of the equation of relativity is basically that on one side you have basically space-time. So this is what describes the landscape of our universe. You can think of if you live on Earth, right, and you don't sort of you cannot fly, you're just walking. You have like a certain topology, right? So you go, some places are flat, some places are valleys, you have mountains and such. So our universe is a bit like that. So our universe is not just flat everywhere, but there's kind of like hills and holes and valleys. And so that's the structure of our universe. And then on the other side is basically the content of our universe, the mass and the energy. And the two are equal. So basically, if you put matter somewhere, you basically end up creating some sort of deformation in the shape of our universe. So the typical way that we see it is something like that, right? So this sort of like trampoline or stretchy fabric of the universe that I was describing earlier. So imagine the sun, right? And it's like sitting there, like, pretty much at the center of our solar system. It basically stretches our universe and it sort of makes a sort of like cavity in this fabric of space-time. But to represent this sort of like, cavity, you need to basically use time as this sort of like vertical dimension. So for us to, properly imagine this sort of like, kind of like cavity with the 3 dimensions of space plus the 1 dimension of time is more or less impossible. Okay, so normally what we do is we remove one of the spatial dimensions and then we represent the vertical axis to be sort of like the time axis instead. So then if you have a star that's in here that emits light, light will basically just follow this fabric. So if it's flat, light will just travel in a straight line. But then if it comes near an object that is massive, like the sun, then the space-time actually is curved. So just like a marble, right? If you take a marble and you toss it right on a surface that's curved, the marble would change direction and would kind of like swing, and change direction. So light will travel from maybe, a while quite in a straight direction. And when it comes like close grazing to the sun, might get deflected a bit because of this curvature in the space-time. So from Earth, it would look as if the star is located there instead of there. And this actually happens for real. Obviously, it's difficult to see because right in the daytime, we don't see stars. The sky is blue. You would need to go to space to see it. However, if there's a solar eclipse, a total solar eclipse, then the moon masks the surface of the sun, and then you can see the stars during the daytime. And this is what happened in 1919. Arthur Eddington and other scientists basically went to observe solar eclipse and measure the position of stars, and they saw that the position of star was deflected when the sun was near, the direction of these stars, compared to later in the year, right, when the star moves across the sky and these stars are like visible during the nighttime. So this deflection of light was one of the predictions that was made by Einstein. There's something else that's really strange in gravity and relativity, because acceleration is completely equivalent to gravity. So imagine that you want, you're a prankster and you like practical jokes and you want to trick a friend of yours. So you put them in some kind of a container that's got no window, and then you put them in some kind of a space shuttle, and then you send them into space, and you make that shuttle basically keep, accelerating. So it goes faster and faster and faster. And the acceleration you give to that space shuttle, you make it go at exactly 9.8 meters faster every second. Okay, so so basically it's exactly what we call the gravitational acceleration on Earth. So the person in it could be standing on the, sort of like on the bottom surface of that shuttle, and could be playing like basketball or whatever, and the ball would go up and down, and they would feel kind of like pulled down to the floor, exactly as if they were sitting on Earth. And they would not know that they might be between Jupiter and Saturn, in in the empty space, and you've just like, send them abroad to never come back, perhaps, or something. Meanwhile, the friend could also be right on the ground in the same container, playing basketball on Earth, and would not see any difference. Okay, so basically, all you need is your shuttle to go faster and faster at exactly the same speed as a ball that you let fall would fall on Earth. So the same gravitational acceleration. So it's really strange, because then, it starts it's quite mind-boggling, because you can sort of create artificial gravity, more or less, right? And according to the laws of physics, everything is the same. So if you like, space, science fiction and things like that, you often see, right, the people in these like space station of the movies and whatnot spinning, right? And they spin so that they're accelerated outward by this centrifugal force, and they make the device spin at exactly the same, at the right rate, so that they accelerate outward just like they would, a ball, or that were like accelerating down on Earth. So that basically they sort of feel artificial gravity. Okay, so Einstein's theory can explain that. Okay, so that's basically all you need to know for tonight about relativity. So I'm sure anyway, your mind is pretty, starting to feel a bit mushy, perhaps, with all these like, crazy things that can happen. So now let's see how we can test gravity and test Einstein's theory with pulsars. And now you see why I talked about binary pulsars earlier. If you have a binary pulsar, you basically have a very accurate watch, what we call a timing or frequency standard, right? So if you have a stopwatch, you can measure how time flows. The pulsar is like a time watch, a stopwatch, right? Because it spins and it flashes, and the rotation is extremely stable. This pulsar, PSR J1713 plus 0747, is the pulsar for which we can measure most accurately, out of the 3,000 or so known pulsar, the rotation for. And basically each rotation we can basically measure with and predict, to not only measure but also predict, to an accuracy of something like tens of nanoseconds. So for instance, if you tell me a date in time, like, I'd done like the calculation at some point, like a couple years back. So 16th of June, 2014 at 8:10 a.m. Universal Time, the pulsar rotational period, right, the speed at which it rotated, was 4.57013652863777, and the last number is uncertain by +3 or -3 milliseconds. Okay, so that's how accurate I can tell you. And then we can take today's date and we could just tell like how the spin period is, because as it turns out, the pulsar is slowing down over time, but the behavior of the rotation is so well characterized that we can predict any place in time what it's going to be. So it's really amazing. So we have like a perfect clock, basically. And by the way, some pulsars like this one are so accurate that on a long time scale, they are actually more accurate than atomic clocks. So we're working on ways that we could potentially use multiple pulsars all together and combine like their kind of like times to actually define a new time standard that would be the pulsar's time standard instead of the atomic time. Because on decades length, it would be more accurate than atomic clocks. On a short time scale, atomic clocks are better because pulsars have a bit of noise in sort of like their behavior. But on long time scale, it's actually very stable. So, okay, so we have a stopwatch. The other thing is that pulsars are very tiny objects, right? A pulsar is about, the size of a city. So what happens, if you take an object like the Earth that is not very compact, right? And has a lot of very soft material, like oceans, for instance, and you get it close to another body, like the moon. Well, you all live by the coast, right? You know what happens twice a day? Tides, right? And that's because the Earth is elongated, right? Is a bit elongated, like not quite as extreme, but a bit like a rugby ball. And the elongation is basically mostly like the water that's been displaced in direction of the moon. So as the Earth rotates, right, the location where the water is displaced will change, and twice a day actually it will do so. So that gives rise to the tides. So when you have tides and things like that, then the physics of the motion of objects is very complicated because things get really messy very quickly. Like depending on how the continents are made and whatnot, then the object like the Earth will slow down, and then it will also slow down the moon, and then the moon will try to adapt, and then the orbit will widen, and it just gets really, really messy. But if you have a pulsar, and let's say you give it another pulsar as a companion, so two tiny objects, they're so dense that you just can't deform them unless they touch, more or less. Moreover, you can take these two objects, right, that are more massive than the sun, and you can basically get them within kilometers of each other. So then you can reach gravity that is immense. So one thing you can do with the binary systems is basically you can use the what we call the Doppler effect, right? So you've probably heard, when ambulance and other emergency vehicles come close to you, right, towards you, the sound they produce is really high tone, high frequency, and then when they go past you, the frequency gets lower, right? So it's like dee doo dee doo, and then once they're past, it's more like doo doo doo. So this effect is called the Doppler effect, and we can see this change in the rotation of pulsars as well. So if you have a pulsar that's in a binary system, just a bit like galaxies are redshifted, right? The galaxies that go away from us, they look more red, and the galaxies that come towards us they look more blue. We can see this sort of red shift and blue shift. So if you have a pulsar that orbits another object, the period that we measure, right, that rotational period I was talking about, that we can measure extremely accurately, it will blink a bit faster when the pulsar comes towards us. It will blink at a higher frequency. And then when it goes away from us, it will blink a bit more slowly. And then this will just repeat over and over, right, as the pulsar comes closer and further away as it orbits the companion. So with pulsars, we basically have a really good way of measuring the orbital motion. And this is what we need basically to measure gravity, right? Because gravity is what makes objects orbit. So therefore, we can measure the laws of physics by measuring the orbits of pulsars. The best one probably so far is the one that we call the double pulsar. It was co-discovered by colleagues of mine at Jodrell Bank, actually. I was still a PhD student back in those days, so I was not here yet. was still in Canada back in those days, but they found the first system that is made of two pulsars that orbit each other. So one orbit around the other one. The distance, the separation between the two of them is about the same as the Earth-Moon distance, but each of them is about 1.5 times more massive than the sun. So you can imagine how gravity is strong there. One of them takes 23 milliseconds for one rotation, while the other one takes 2.8 seconds for one rotation. And because of the immense gravity, it orbits in only 2.4 hours. Okay, so it's really fast orbits. What happens is the system is effects that we see, for instance, in the solar system are magnified. You might have heard of Mercury's orbit precessing over time. So if you didn't know, Mercury's orbit is not a perfect circle around, the center of mass, like the point of equilibrium between the sun and Mercury, but rather the orbit is a bit elongated. It looks a bit like an egg shape. And this egg shape, actually, an orbit after another, the direction of the elongated part of the orbit tends to drift from one orbit to another. So if you didn't have the effects of relativity, like according to Newton's theory of gravity, for instance, the orbit would stay in the same orientation over and over. So the orbit would stay, say, like that, upright. But then because of relativity, the orbit actually drifts over time like that. For Mercury, the drift of the orbit is 43 arc seconds per century. So basically, after 100 years, the drift from this point to like the elongated point after 100 years is less than 1 degree of drift. So it's very, very tiny. But French astronomer Le Verrier actually discovered this effect in the Victorian days, because we had like good enough observations over centuries from various astronomers that he realized that Mercury's orbit was not a perfect circle and drifted like that. Now, Einstein was the first one to explain why this was happening. And in the double pulsar system that I talked about before, it's not a fraction of a degree per 100 years. It's 17 degrees per year that this drifting takes place. So it's massive. And that's just due to gravity being so strong. Then something else that happens is that objects that orbit each other, they actually move matter around space, and therefore they produce and they release energy. So if you take an object and you make it orbit another one, it will release some of its energy. And the energy comes from the orbit itself, like what we call the binding energy. So it comes from essentially the gravitational pull from one object to another. It will be dissipated from there. So if you take, like, for instance, the Earth around the sun, the Earth produces just about 100 watts of energy from its rotation about the sun. Like, that's the amount of energy that is lost from the gravitational energy between the two. So over time, in theory, the Earth will get closer and closer to the sun. Now, in practice, this will never happen because there's like the moon and other things that happen, and then the orbit of the Earth is not necessarily shrinking. But if you take the double pulsar system, the two objects, which I said are separated by about the Earth-Moon distance, it turns out that they're shrinking. The orbit is shrinking because of the energy that's produced from the orbital motion. And the amount of energy is so large that the distance shrinks by something like 7 millimeters per day. So just about 1 centimeter per day. So, it's a couple of meters per year. So if you take, that distance, Earth-Moon distance, and you shrink it 1 centimeter a day, in about 85 million years, the distance would be 0. So these two pulsars would actually collide, within, sort of like age of, since the dinosaurs disappeared, more or less, something of that order of magnitude. So when this happens, you'll have like these two super, compact objects that will collide, and this will produce a lot of, fireworks. We call these events gamma ray bursts, and they've been observed for, a couple of decades now. They're extremely energetic, and when they happen, also it produces a lot of ripples in our space-time. So you can sort of picture, that space-time I was talking about before, like this sort of like fabric, right, of the universe, which is kind of like, already distorted, right, by the field of the objects that, like, creates a bit of a cavity. But then when they collide, it's a bit like if you were to throw a rock in water. So it creates a huge disturbance in the fabric of our universe, and then the fabric, like the space-time itself, like basically jiggles around, and it will dissipate over. So it's just like dropping a rock or a pebble in a lake. You have like this ripple, and it propagates, and then at the center, right, where these two things collided, a black hole will form, and then things will become quiet again. So, and we can detect these ripples in space-time now. We've done it with that LIGO observatory. So we'd be using very advanced lasers and things like that. We could actually measure these ripples in space-time. Okay, so now we can see all these really strange effects, basically using pulsars in orbit with other pulsars or other neutron stars, because of the huge gravity. And in the solar system, these effects also exist, but they're very tiny and they're very difficult to measure. Whereas in the pulsars, because the gravity is so large, these things are become immense. So what we can do is basically we can test the gravity, right? We can test an Einstein's theory, which describe how space-time behaves. We can test it to a much better precision than what we do in the solar system. But also, and now don't get too obsessed with this figure here. The idea is it's just to sort of like display measurements and this concept of measurements. It's an actual figure from an actual paper. But what it says is basically that there are some theories, some very special theories of gravity, not Einstein's theory, but alternative, competing theories, which in the solar system make the exact same predictions as Einstein's theory. But then when you go to a really strong gravity environment, then these theories, they will not predict the same thing as Einstein's theory predicts. So when you go to really the most extreme, that's where you can tell them apart, basically. And so, we make the measurement, and then we test if like gravity behaves the way that Einstein predicted or some other theory predicted. And then we see who's right. And basically what we concluded so far is that Einstein was always right. I should say, and that's the cartoon that's there, that Einstein was always right, but according to his theory of gravity, because he could have been wrong about many other things. Okay, like this joke here, like saying that the best sandwich, that it's impossible to find a good sandwich in town or something. But basically, so far, Einstein's theory has always worked perfectly with every single test that we've made, including that of pulsars, which are now the best and most accurate tests. So back when I did my PhD around like the turn of the millennium, so something like 20-ish years ago, the theory of Einstein had been tested to about this sort of precision. So that's basically 0.05% precision using pulsars. And now actually it's improved, and we're about a factor of 1,000 even more precise. Okay, so all the tests basically agree with Einstein. So it's kind of annoying because basically Einstein is, is always right, but we sort of know that maybe it fails at some point, because we know that the theory of Einstein to explain gravity, it doesn't work to explain how particles behave on the very tiny scale, on the quantum scale, as we talk. We need a quantum theory for that. But we know that like theories should explain the very little to the very big, all together. So we don't really understand why that's happening. So I'll just take some questions now. I think I'll leave you with this sort of as I start like fielding questions, this little video that shows the double pulsar system. So it's an animation that we had done back when we found that pulsar with another pulsar that orbits it. So basically what we normally see with the telescope is just two flashing lights that are exactly at the same position. And this is just an animation, right? So we never see these actual objects like that. But basically, one spins very fast and we see it blinking quickly, and the other one blinks more slowly. But in this particular double pulsar system, one actually passes in front of the other one as well, and it creates eclipses. So the one that's behind actually gets hidden temporarily. But it doesn't. These eclipses are unlike the solar eclipses, where the moon passes in front of the sun, and it's the surface of the moon that screens the sun. In this double pulsar system, it's the actual plasma, like it's the actual cloud of particles that surrounds it, that screens the one from behind, rather than the surface of the object itself. And so we see the light disappearing for about 30 seconds when one of them passes in front of the other one every 2.5 hours, every orbit. And so we have basically, some shadowing kind of event that we can observe. And by observing the shadowing, we can actually also tell that the axis of rotation of one of these two pulsars is actually wobbling, just like a spinning top over time. And this wobbling effect was an effect that was actually predicted by Einstein as well, but had never been observed until 2009, basically. And that was when I published those results on this wobbling effect. So that was the first time we could observe stars wobbling like that. I mean, there are other types of effects like tides that can make a star wobble, but like in these types of stars, like that, due to gravity, that's the first time we could see that. Okay, so yeah, so basically pulsars, extreme objects, and Einstein's theory describes how the motion and time actually takes place in our universe. And by measuring the motion of pulsars, we can see that this motion is not the same motion that's predicted by Newton's theory, and it follows Einstein's theory super well. I think there was a question from Lee Edwards about how useful are multiple pulsars as gravitational wave detectors. So that's a current field of research. That's something that us at Jodl Bank are very active with. So you can use multiple pulsars, and you can measure like the blinking of these pulsars, and you can basically use it. I said earlier we can use the pulsar timing. Right, we can use the measurement of the rotation as like very accurate clocks, more accurate than atomic clocks. But the other thing we can use them for is basically to triangulate our position in our galaxy using the blinking. So because if we move one way, right, we'll get closer, closer to some pulsars, but some other pulsars will go away from them. So it means that if we're moving relative to many pulsars that surround us in the galaxy, if we move, some of them will appear blue shifted and some of them will appear red shifted. So we can triangulate our position extremely, extremely well. And the idea is that if some gravitational waves pass at Earth, it will basically swings the position on Earth by basically the width of atoms or less. But actually, we can triangulate ourselves so well that we could actually detect this. And so far, we've done it using lasers on Earth with instruments like LIGO. But we can but these instruments, they only detecting gravitational waves from like black holes that collide and neutron stars that collide. Whereas the gravitational waves that we could detect with these pulsars, there would be longer wavelength gravitational waves that would be produced by the merger of galaxies, like the supermassive black holes in galaxies. So it's completely different types of things that we could detect with them. Then I can see a question from Mike. Can a accreted material in a binary cause a pulsar to become a black hole? Yeah, that's a really good question as well. Indeed, we believe that this may happen sometimes, right? In that little video I showed earlier, I'll just get back to it. Right, in this little video here, I basically said, yeah, like matter, is accumulated on the pulsar and it makes it spin faster. So if you accumulate too much matter, the density on the pulsar will increase. And then if you reach a limit, basically where the pulsar mass is, we don't know actually what that limit is, but it's somewhere between 2 and 3 times the mass of the sun. So if the pulsar mass goes beyond that critical limit, the star will collapse. So basically not even like these neutrons that I said are super tough, and could hold extreme density, even these neutrons could not resist the gravity, and the star will collapse and turn into a black hole. So we think this may happen every so often. We've never really seen it happening from just a regular star giving off mass, like in this video. But certainly if two neutron stars merge, one with another, some of the matter will just sort of like explode. But overall, most of the mass will be, the two of them fusing basically. And then you typically reach a mass that will be beyond, that threshold mass that forms a black hole. So that's an extra way of forming a black hole. Like the black hole can form straight from like the star exploding, like the very big star exploding, but also it can form if you take like, say, two neutron stars and you merge them, or you take a neutron star and you dump a lot of matter on top. Norman is oh no, actually no, sorry, David, I think your
That's
name
right,
is it?
David.
Yeah. Can we detect pulsars in other galaxies? Yeah, only a few so far. So the pulsars we've detected in other galaxies are located in the Large and Small Magellanic Cloud. They're the only other galaxies in which, beyond ours, the Milky Way, in which we've detected pulsars so far. I mean, there's no doubt that pulsars do exist in, the Andromeda galaxy and just about any galaxy out there, because if stars evolve and explode, they will form pulsars, some of them. But it's just that the other galaxies are too far and our instruments are not sensitive enough to detect pulsars in them at this point. But there's a telescope I'm working with. It's called Meerkat. It's just been commissioned over the last year in South Africa. It's located in the Karoo Desert in the northwest part of South Africa. There's 64 dishes, a bit like mini Lovell telescopes if you want, but each of them is much smaller. It's only 13 meters in diameter, but there's 64 of them. So altogether, they're more powerful than the Lovell telescope, as it turns out. And we point them, in the sky. We just found 5 new pulsars recently with it. And one of the projects is actually to point and do a complete scan of the Small and Large Magellanic Cloud, because the sensitivity of that telescope is something like an order of magnitude better than the best telescope in the Southern Hemisphere, which is the Parkes telescope. So we're expecting to find, hopefully, like all pulsars that lie in these 2 satellite galaxies of ours. But also there's an extra project. We cannot look at M31 because it's too far north, but we can actually look at other galaxies from what we call the local group. And we're hoping that we can detect pulsars in those galaxies. And it's going to be really interesting because other galaxies, they don't have the same composition as our galaxy. Like, they don't have the same mass, they don't have the same amount of metals. And so it's going to tell us a lot about, like, how many we find in them is going to tell us a lot about how stars evolve in different metallicity environments and things like that. So it's really important to understand the life cycle of galaxies. So that's coming up. And then with the next generation telescope, the Square Kilometre Array, which the UK is, at Jodrell Bank, we're hosting the headquarters of the SKA organization. It's going to give us like pretty much like an order of magnitude sensitivity, then we think that we should be able to find every observable pulsar of our galaxy. So we think that, right now we know something like 3,000. So we think that we can detect. So it doesn't mean that they could be pulsars, but they're not pointing at us, right? So we could not detect those. But the ones that could point at us but are just too faint, we think there's probably between 20 and 100,000 in the galaxy. So we're probably going to detect all of them, and we're probably going to detect a lot of them in like fairly distant galaxies as well. Okay, other questions. Yeah, another from Lee. Is there an exotic object between a neutron star and a black hole out there waiting to be discovered? And when do we expect it? And I'm pretty sure, yeah, if we detect one, there would be most certainly a Nobel Prize. It's actually difficult to tell, and it's actually one of the very interesting things about studying neutron stars, or pulsars for that matter, because black holes, I mean, they're quite interesting for some tests of physics, but overall black holes are rather boring. They don't emit light, so they make the light, the studies very difficult, because we can only study their shadow, from the matter that falls onto them, or the motion of objects near them. Whereas the pulsars, they emit light themselves. So we can measure a lot more things and a lot more accurately than black holes typically. And it turns out that we don't know that much about the internal composition of neutron stars. We know they're mostly made of neutrons, but actually our laws of physics, like our understanding of nuclear physics and particle physics, which is what's needed to describe, what happens to matter at high density, is not good enough. So we don't even know what's at the center of neutron stars. So it could be that these objects are made entirely of neutrons, like some kind of a soup of neutron, atom particles throughout. But it could also be that somewhere inside the neutron star, these neutrons are breaking apart and turning into their elementary particles, which are called quarks. So it could be that inside, at the core of neutron stars, it's actually some kind of a ball of like a core made of quarks. But also it could be exotic particles. There are particles that are called iprons, and there's other types of weird particles that also have been theorized to maybe exist, but have never been observed. So it could be that these exist at the center of neutron stars. So we're trying to actually measure the size of neutron stars and their masses and try to map their mass and radius, because if you can map that, you can essentially try to work out how the inside is exactly. But it's very difficult, as you can imagine, right? I mean, we cannot just go with a measuring tape and determine how big they are. So we're hoping to learn more about like fundamental physics really by studying neutron stars. And it could be that there are such things as like stars that are made only of quarks, for instance, or exotic particles. But so far we have no evidence of that. And maybe one day we'll be able to, but what we'll need to do that is more or less measure the mass and the radius, I think, of these objects that we think are neutron stars. And maybe we'll be able to tell that actually some are not neutron stars, because these objects would also have magnetic fields. And so from far away, they would look like neutron stars. So it's only when we measure their physical parameters better. So who knows, maybe with experiments like the ones at CERN, right, at the colliders, maybe we'll learn more about particle physics and nuclear physics that will tell us if these things exist. But it could also be that astronomers will figure it out before, and then we'll tell the particle physicists, to look for these particles. So we're kind of like, we're not really competing. We're like kind of trying to prove physics in different ways. So is there a known life limit to a pulsar? Not really. Pulsars are essentially the ultimate, kind of like state of matter for these objects that have exploded. So once they're formed, you have the object and it will not change size over time. Initially, they're very hot. They would be sort of billions of degrees, the temperature of like, the center of a star, basically, because it's lost the envelope. So it's the core, it's the naked core of a star that, shrinks. So so they do get, you know, colder over time, but except for cooling down, nothing more happens. They will also slow down, so that, you know, when they're born, they can spin, you know, tens of times per second, and then they get slower and slower. And eventually, I guess they would stop spinning, but that would take, you know, hundreds of millions of times the age of the universe. So basically, you know, in we've the Crab pulsar in the Crab Nebula, we observed a star exploding in 1024 after you know, of our era, so 1,000 years ago. Sorry, 1054. So it's a 1,000-year-old pulsar, and that one has slowed down by something like, you know, less than a fraction of a millisecond in 1,000 years. So so it's gonna take, you know, hundreds of millions of years for the pulsar to be as slow as, like, you know, a minute, for instance. However, we think that pulsars, we only see them for something like a few tens or hundreds of thousand years, maybe a million year at most. And it's just because at some point when they slow down, if they're slower than like 10 seconds or 20 seconds or something like that, the light that they produce, the radio light, stops being produced. Like it's typically produced, it's a bit like a dynamo effect, if you want. So the star doesn't spin enough, you know, this magnet does not spin fast enough to produce this powerful radio light. So so yeah, so eventually pulsars, they kind of, like, you know, the spark sort of dies, and then they just become like a neutron star, but they don't pulsate anymore. Yeah. So is the surface gravity of pulsar great enough to create a time dilation? And could we detect it if we did? Yes, very much so. The just trying to the time dilation would be something like, it would change the wavelength by something like 15% or so, 15 to 20%, if I recall. So, you know, light that would be sort of, I don't know, greenish light at like what, like 600 nanometers would look like probably 800 nanometer light or something like that. I would need to calculate, you know, I'm just saying that like off the top of my head. So I would need to, you know, obviously double check all my numbers. I know it's recorded, but so don't, you know, don't quote me, like, you know, don't quote my life on it. But if I recall, that's something like a 15% effect or something like that. So it would, yeah, so blue, you know, sort of green light would sort of turn into kind of like a red light. The only thing is that basically neutron stars or pulsars, they don't produce emission lines, you know, like a regular star, right? So if you look at the sun, you can see absorption lines, or other stars, they will show like Balmer lines or things like that, and then you can measure the redshift. But basically pulsars, if you look in the optical, all you see is like pure black body emission, like it's completely like smooth. And so so then you cannot quite measure very well the this sort of redshift. There's other ways we can do it using X-ray observations and some, but I won't get into much details because that would take probably too long. I mean, I can expand later if some are interested, but but we do detect, and that basically the redshift, right, depends on how compact the neutron star is. So if you know the mass and the radius of the neutron star, you can tell what the redshift would be. So actually measuring the redshift is something that enables us to basically measure the radius of the neutron stars. And that's pretty much like the only way we can do it. And so, but it's extremely challenging. So, but that's kind of how we do it. So yeah, so that was the last question, I think, that was in the list there. So I hope it answers it well.
Yeah, well, Rennie, thank you very much indeed. And Bob, would you like to give a vote of thanks?
Thank you very much.
Thank you, Rene, for putting over such a complicated issue, really, in a short period. So thank you very much. And perhaps we'll keep an eye on what you're getting up to in the future. So everybody
Yeah.
clap.
Yeah. Thank you.
Right, thank
Thank you
you.
so much. I hope I didn't lose you all during my explanations. Was it okay?
Yes, yes,
was-
Obviously,
Yeah.
very
I'm
good.
not assuming that you will remember everything, but hopefully some of it.
Best description of Einstein's theories I've heard. So thank you for that.
Yeah.
Right, folks. So
Okay.
many thanks for coming along this evening, and many thanks to Renee.
Yeah.
And we hope to see you all again in a month's time. I've forgotten what date it was, but did I say February the 8th?
Yeah.
Don't forget, we're open every Friday evening on Zoom for the observers and our main call at 8:30. And don't forget, of course, Lee's cosmology group and Keith's history group. So anyway, many thanks everybody for coming. Stay safe and see you all again soon.
Okay. Thank you, David.
Thank you, Renee. Thank you, David.
Bye.
Thanks, David. Thanks,
Renee.
Renee.
Thank
See
you.
you, Bob.
All right.